Welcome back, my structural analysis friends. In today's video, we're going to be looking at influence lines for girders. You'll notice some similarities between the methodology for trusses that we did in our earlier video, but there are a few differences that we're going to take a look at. So without further ado, let's get started. When looking at influence lines for girder systems, we first need to define what a girder is. And basically, a girder is a member that carries other members, which may in turn then be supporting other members. In our definition, or in our example for today's lecture, we're going to be looking at just a simple basic girder here that is being supporting, in this case, 5 beams located at these I-beam location marks across the top, and then on top of that is some sort of slab or plate, which is now the travel surface. So our point load, imagine this is like a bridge deck or something. The load comes in across here and then it steps onto the girder and it travels across these plates. But because of the way the plates are supported, the girder feels something a little bit differently. All right, so we've got to kind of figure out what we're doing. Now, if you remember back when we were doing trusses, we had a similar phenomenon by which we were moving point loads out to panel points. Okay, and this is no different. Okay, we kind of do the same basic game. In fact, this will look very familiar if you've watched the truss video. Okay, so what we have is so let's imagine we look at an arbitrary panel, which is this rectangle here. Okay, that's located at some distance delta x from a reference. So usually we take the reference as the left side, and that's what we're going to do here, but for now that's what this dotted line represents as the reference. Okay, and then our point load, or one kip load, can be anywhere at once along that panel. Okay, so we're going to say that the distance from the point load to the end of the panel that it's sitting on, we're going to call as x prime, and as we've always done before, that the point load is located at a distance of x from my reference. Okay, so this x never changes. Now, if my panel is the one to the left, x is still being measured from the reference. If it's the one to the right, it's still being measured from the reference. Okay, now if we go with our basic derivation, we've showed in previous videos, and if you need to go back and look at that, then feel free to do so, that the reaction at the left end of this beam that we're going to call as RL is equal to 1 minus x prime over LS. Okay, where LS is the span of the panel. And so if we do our math and kind of do a quick substitution, we can write that this is 1 minus delta x all over LS becomes the left reaction. And then the right side reaction is x prime over LS, or x minus delta x over LS. And if you remember, we called that delta x as the offset, and that will be, usually it's the lower bound of our limits when we start to quantify these equations, and I'll show you more as we get to going. Now, that panel with its, we've now taken the one kip load and turned it into support reactions on the slab, and of RL and RR. Well, those two guys then apply 2 point loads down to the girder below. Okay, and so this is where we have to kind of, things get a little bit different. Before, when we were doing just beams, we only had a single point load that we were looking at, but now we have multiples that are coming as a result of this slab spreading load around. Okay, and so that's kind of the basics of our free body diagram that we're going to be looking at. Now we're going to do some manipulations, and in fact we're going to jump straight to an example since you've seen this before in trusses. Like I say, if you need to go back and look at it again, please go back and rewatch that video, but for now we're just going to kind of set this problem up and kind of see what we can find. All right, so we're going to look at an example in this case that is just it's a girder. Now, it's not a simply supported girder. It's actually got a cantilever end over here on the left. Okay, so it's a little bit more interesting. We have a roller at B, we have a pin at E, and then we have 4 panels that are loaded onto transverse beams, or these I-beams here, that are spaced at 10 feet along the length. Okay, and so my one kip load can travel anywhere that it wants along the top of these panels. Okay, we're going to set our reference as the free end of A, and so we'll measure X off of that for all cases. So as with any structural analysis problem, the first thing that we do is we're going to go figure out, well, what are my support reactions as a function of X? Okay, and so this free body diagram is kind of interesting. The panels don't affect the support reactions. Okay, we're just moving a single one kip point load around. Okay, and because I don't cut anything out, the slabs, I would have an RL up on the slab, and that same RL would match on the girder. They cancel each other, so they don't show up on the free body diagram of the entire structure. Okay, so our simple diagram for the support reactions is very easy. It looks something kind of like this. One kip X from the left end. Again, this is my reference. At X equal to 10 feet, we get a BY reaction, and then 30 feet later, we get an EY reaction, or 40 feet from my reference. Okay, so if you do your structures and your statics, and I'll assume that we're pretty good at this by now, but if we go through here are the equations on my free body diagram, pull that down a little bit, we have one kip times what would be, I'm going to sum moments at B in order to, or at E in order to find the reaction at B. So it's one kip times what would be 40 minus X, okay, minus BY times 30 will all equal to 0. That's the statics equation. And so I can solve for BY, and that tells me that it's one kip times 40 minus X over 30. Okay, now we can test this and make sure that our ideas are sound. If X equals 10, it means the point load is sitting over the support at B. The reaction at B should be 1.0. And if I plug in X equal to 10, that's the value that you get. And likewise, if X is equal to 40, which means the load is over here, on here, my reaction at BY should be 0. So if we plug in X equal to 40 into this equation, you do indeed get 0, so that one checks. Okay, so the BY equation seems like it's pretty reasonable. Okay, we can do the same thing to find the reaction for EY. In this case, I choose to sum forces in the Y direction, so it's BY plus EY minus 1. I can solve for EY as 1 minus BY, and then the BY, we just use the equation from before, and so my equation looks like 1 minus 40 minus X over 30. And in this one, if X equals 10, EY is 0 because that's the point load over B, so there is no reaction at E. Okay, and then at X equals 40, EY is equal to 1. So again, we check with what we know about loads when we were doing Mueller-Bress law and those kind of things. Again, if you're struggling with this or you don't remember, go back and take a look at the video. All right, now we can go in and we can start looking at, well, what's happening with these point loads? So the first one that we look at is the case where X is between 0 and 10, meaning that it's on that first panel. Okay, our offset delta X is equal to 0, and this is the load on panel AB. Okay, so the loading on the girder, if I take the panels and that point load off, turn into a reaction of RL and a reaction of RR acting at those locations. So RL is located at the end at X equals 0, and then RR is located 10 feet away, which puts it directly over the support BY. Okay, so that's our full free body diagram. Now, our reactions in this case are 1 minus X over 10 and X over 10 for RL and RR respectively. So these should be no surprises by now. Okay, so now to find the internal effects, what we're looking for in this example, we're looking to figure out what is the influence line for the shear and what is the influence line for the moment as we start to kind of look at this. Okay, and so in order to see those, we have to cut. And so I've drawn both sides of the free body diagram. Okay, and so for the left piece, RL and RR are at the locations they were, BY is where it should be, and then at this cut line I now get a moment MCD that is counterclockwise, which is positive by our sign convention, and VCD, which is positive downwards on that side. Okay, so we're using the beam sign convention that we used as before, as we outlined. Okay, and then if I draw the other side of it, then I get the opposite MCD going in the opposite direction, and VCD opposite now going up, and a reaction of EY acting on that. So these are our two free body diagrams. It doesn't matter which one you work off of, you'll get the same equation and the same values. Now if you look at these, one of these is clearly a little easier to work with, and I would suggest that it's this guy, right? Because I got all these RLs and RRs and all of those have X's in it, and doing the algebra, it's not hard, but it's a little cumbersome. So we're going to take the easy way out and we're going to write the equation to this. All right, so all I'm going to do then in order to get the moments and the shears, let's do the moment equation. I'm going to sum the moments at what I'm calling as point F. Okay, so point F is considered to be the midspan of the beam. So this is 15 feet here and this is 15 feet here. Okay, and so that's what we're looking for is the values of moment and shear, or what we're calling MCD and VCD is actually what's happening at F. Okay. All right, so that's what all I'm going to do then. And so off of this equation, I get, if I go sum of moments counterclockwise positive, EY is a counterclockwise moment, so it's EY times 15 minus MCD, and then VCD is times 0, so we won't even write that in the equation. All right, and so if I write that, then the equation for the moment on this interval of 0 less than X less than 10 is given here. It's 15 times 1 minus 40 minus X over 30, and that's our value for MCD. Okay, likewise, I can do the same thing for the forces. VCD plus EY equals 0. So VCD is a negative EY, and so that's now 40 minus X over 30 minus 1. Okay, and we'll get us the shear at that location. Okay, and so those are your equations for that first interval. So let's just test the boundary conditions on these, just so we can get some numerical values. At x equal to 0, the MCD value is actually -5, and the VCD is +1/3, or 0.333. Okay, and then at x equals 10, the moment is 0 and the shear are both 0. And again, think about where this load is at x equals 10. It's sitting right over the top of this support at BY, because that was 10 feet. And so there will be no shear or moment felt, because all that load is going straight into the support at BY. Okay, all right. Now, part of that is because that's also where I have a reaction. Okay, all right. So now we can go back and kind of continue on, same basic game. So what happens is we now go from 10 less than x less than 20. Our delta x is now 10. Again, it's this lower bound limit value here. Okay, and so my free body diagram of the whole system now looks like this. It's very similar, except now RL and RR have moved over on this thing. Okay, and if we look at it, we can draw our free body diagrams again. That's what this has done. You know, RL and RR have shifted over. Everything else is the same. And if you look at the right picture, it's exactly the same as what we had up here. It's the exact same picture as this guy up here. So if that's the case, then the equations are exactly the same. And so we can save ourselves a little bit of time and basically plug in equations for 10 and 20, and that's what I do at the top of this page. Okay, so at x equals 10 feet, moment is 0, shear is 0, that's what we expected. At x equals 20, the moment is now +5, and VCD is now -0.33. All I'm doing is plugging in x into those equations that we had from before. Okay, all right, so let's go through to the next one. The next one, things get a little different. Okay, so now we're looking at, here's my point F, and now RL is located at 20 feet, which is this location, and RR is located at 30 feet, and you can see that it straddles that point load. So when I go and I cut my beam through F, now RL is on this one, but RR is showing up over on this one, and they're both 5 feet away from the location that I'm interested in. So this is the difference in it. The hardest part of this is getting these free body diagrams drawn right. So if you can sketch these, then the rest of it's just simple statics. Right. So if I do that now, so now it's kind of a question of which one do you want to work with. I'm still going to write the equation to this. No particular reason. I think the algebra is a little bit easier because EY is a little simpler, but we're going to write it the same way that we did before. So the sum of the moments at F is equal to 0. And so I'm going to do, we're going counterclockwise positive again. So that's minus MCD. Okay. And then that's going to be minus RR times 5 feet plus EY times 15 feet. So it's this term here that shows up and that's new to us. Okay. So now, one thing that we've got to account for is the RR equation, all right? So remember, our offset is 20, so our RR for this is x minus 20 over 10, and that's what's going to get plugged into our equation down here. And so that's all I've done is I've plugged in RR, x minus 20 over 10, multiplied by 5 feet, okay? And that is, there's a negative sign, got to watch your negative there, okay? And then 1 minus 40 minus x over 30 times 15 is the EY reaction times its distance. And so that's our equation. So if we plug in our values for x equals 20 and x equals 30, MCD is going to be positive 5 at 20, which is what we had before. Okay, and there are no sudden jumps on this, so that makes sense, that checks. And then at x equals 30, then I plug in 30 and I get a value of 5 plus 2/3 of 5, or 20 over 3, which is 6.67 will be the moment at CD when the point load is located at 30 feet over there. All right, okay. So one more section to go. Okay, well actually, let's do the shear, playing the same game. So if I write the equation for the shear, it's now plus VCD minus the RR plus EY. So that's off my free body diagram. I can solve for VCD and do the algebra. So it's x minus 20 over 10 minus 1 minus 40 minus x over 30. Okay, is my equation. And again, these are starting to get a little bit longer, but I can plug in x equals 20 and x equals 30 to get the values. And so VCD here is minus 0.333. Okay, and then VCD at 30 is 1 minus 2/3 or plus 0.333. So you can see that it flips signs in that span, which is kind of interesting. But we saw something similar again when we were doing trusses before. All right, so now let's go do the last one. Again, same game. Okay, 30 less than x less than 40. Our offset is now 30, so my reactions are now 1 minus x minus 30 over 10 and x minus 30 over 10 for RR. Okay, so the only thing that changed was this last term in all of these. Okay, and then the position of the load has now moved so that RR is now sitting over the top of the support, and then RL is sitting at 30 feet from the left. Okay, and then by is still the same, ey is still the same, my point F is still in the same location. Okay, so now same game, draw the free body diagram. I'm going to cut it at F, and so now there's no RL or RR on this piece because they've now moved both of them over to the other side. Okay, and so if we do that, we can come up with our equations accordingly. I'm going to argue that this one is simpler to solve, so we'll write our equations to this one. So if we sum moments at F, this is going to be minus B, again counterclockwise positive on the moment, minus by times its distance of 15 feet, okay, plus MCD all equal to 0. And if we plug in our values, that's 15 times by, 15 times 40 minus x over 30. Plug in your values, x equals 30 gives me a positive 5, so that guy matches. And then at x equal to 40, we have an MCD equal to 0. Let me check one thing real quick. And I have a math error. This is not 5. Okay, this guy is 6.67. Right there. Okay, so we'll get that, make that a little cleaner to see. Okay. And that just looks bad, so let's do it right. Equals 6.67. A little cleaner. Okay. And then at x equal to 40, if I plug into this equation, I get an MCD of 0. And again, that should make sense because now the point load's sitting over the support. There should be no moment felt in the interior span. Same thing for shear. Now it's by minus VCD equals 0, so VCD is 40 minus x over 30. Okay, plug in x equal to 30, I get a positive 0.33. That guy matches. And then if I plug in x equal to 40, I get a VCD of 0, which it should be because, again, the load is over the support. All right, so all that's left now is to take all of that data that we've plotted, and that was for 3 spans, and plot the pictures. Okay, and so this is what we get. So here's my beam. Okay, and again, I'm not drawing the panels or the load on this thing, but what happens is that one kip load moves across those panels. If I plot my points, I got a positive 0.333 here, a 0 here, minus 0.33 here, and plus 0.33 here. And then of course 0 out at the end. And so that's the shear diagram for this load as it moves across the panels. Like I say, it doesn't have the jump that you saw in shear before because the loads are being spread out and coming into the location of interest in different ways. But it's just simply a math problem and then plotting the functions. So for shear, you can tell right off the bat that there are 2 places that get me the maximum positive shear. I can put the point load out at the end of the cantilever, and its multiplier is 0.333, or I can put it directly over that support that's 10 feet from the end. Now again, F is sitting here. Okay, so if we put all my point load here, I actually get a bigger shear value. But likewise, if I put it over the support to the other side of it, I actually get the negative of the shear, okay? And so that's how we construct this. Now, one thing that you'll notice on these girders is that before, whenever we did a shear, we always had a jump of 1.0. We don't have that anymore, okay, because we don't have that instantaneous jump. So this is the picture of the data points that we just plotted. We can then go in and do the same thing for the moment, okay, and so my factors were minus 5 here at the end of the cantilever. It was 0 at this support. It climbed to 5 at the next beam location, and then went to 6.67 at the next one, and then came back to 0 at the last support. Okay, and these were our approaches. And so this should make sense because if I put a point load out here on the end of the cantilever, I get a negative moment in the backspan. Okay, and that's what I'm seeing with that negative 5 happening there. And likewise, the maximum positive moment then on the span I would expect to occur somewhere within that span itself. And then again, it occurs such that it's at that x equal to 30 position is the maximum. But very quickly, you can construct these lines and you can quickly see where loads need to be in order to be able to get the maximum effects that we're looking for, in this case, that point F that is up here at the midspan of span CD. So anyway, I know we've gone kind of quickly through that. Like I say, a lot of the math you've seen before. It's just a matter of just basically setting up the pictures and understanding how these loads pass around. Okay. Typically, we look at the panels as being some function of, 2 point loads. Okay, where we have an RL or an RR. If I pull this up like that, but you can also have more complex systems of panels where maybe it's being an indeterminate panel where I have an RL and an RM and an RR, and it's the exact same game depending on what you have to do. Now, we solved this one because it's pretty straightforward. This one, you would have to be able to solve this indeterminate system for a load somewhere on it, but it's the exact same approach. that there will be a function of RL based on the load's position from here, and RM likewise in another one like here. In fact, this kind of idea of being able to take a nodal load or a concentrated load and pass it out to 3 different nodes on a system is kind of an approximate technique that you'll see in finite element method, okay, where we have shape factors and things like that start to kick in that help spread loads around an element. Okay, that's getting a little bit ahead of where we're headed with this topic, but you do this in some advanced structural techniques. For the purposes of this class, we won't, but I just want you aware that you can do it. I can have any number of these, and as long as I can come up with how this load gets passed out to the supports, for all these cases, I could then come around and turn this and load my girder accordingly. Okay, so anyway, I hope that's made some sense to you. It's pretty easy. You just got to draw the pictures and look at what the forces are and where they're acting and get your free body diagrams, and the rest of it's pretty simple, really. Okay, like I say, it's kind of hard for me personally to be able to visualize what the influence diagrams look like, especially when we get into these reversals that happen, but it's just kind of the nature of the beast. I can do the math and I can do the steps and I can always solve it, so that's what we want to take a look at. So I hope this has made sense. If you got any questions, feel free to toss us some comments down below. We'll be happy to answer them. And as always, if the video helped you out at all, please be sure to like and subscribe to the channel, and we will see you next time. Have a great afternoon. Happy engineering.